Design a URL shortener is the first system design question almost everybody gets, and it is far deeper than it looks once you stop reciting an answer, because the interviewer is not checking whether you know what a short link is. They are watching how you move from a vague prompt to a defensible design. So, we will walk the whole thing, clarify, estimate, sketch, go deep on the interesting part, break it on purpose, and then recap the shape you can reuse anywhere. Start with what it must actually do, which is take a long URL and return a short one, and then redirect anybody who visits that short one. Then 4 questions that change the design. Can users pick a custom alias? Do links expire? Do we need click analytics? And is deleting a link required? Now the non-functional side, which is where the architecture actually gets decided. So ask about scale, latency, availability, and consistency, one at a time. The single most valuable question is the read-to-write ratio, because redirects outnumber creations by something like 100 to 1. And that ratio drives everything downstream. Also, settle consistency early, because a brand new link taking a second to work everywhere is usually fine, and saying that out loud unlocks caching and replication later. Now some rough numbers, and assume 1 million new links a day, which with 100 to 1 read ratio gives 100 million redirects a day. 100 million a day is roughly 1,200 redirects per second on average. And if peak is 3 times average, you are designing for about 4,000. For storage, 1 million rows a day at around 500 bytes each is half a gigabyte a day. So 5 years is under 1 terabyte, which is genuinely small. And that is the point of estimating, because under a terabyte means one database can hold it, while 4,000 reads a second means it must not serve them. So here is the whole system on one screen: a client, a load balancer, the service tier, a cache, and a database. And we will walk each block in turn. It starts at the client, which is either somebody creating a link, or far more often, a browser quietly following one that already exists. The load balancer spreads requests across identical instances, and because it is the front door, it is also the natural place to put rate limiting. The service tier, the API layer, is deliberately stateless, so any instance can answer any request, which is exactly what lets you add instances as traffic grows. In front of the database sits the cache, and it gets a whole chapter of its own, because at this read volume it is the most important block on the screen, and the database holds the mapping durably, which sounds like the center of the system, but by the end of the next chapter it will not be. On the write path, a request arrives with a long URL. The service generates a short code, stores the mapping, and hands the short link back. On the read path, somebody hits the short link, we look up the code, and we return a redirect, and this path is 100 times busier than the other one. Which redirect matters more than people expect, because a permanent 301 gets cached by the browser and never comes back, while a temporary 302 returns every time. So if you promised click analytics in the requirements, you have already committed to the temporary redirect. And that is a nice moment to connect back to chapter 2. Now, the deep dive, and the first real decision is how a short code gets generated, because there are 3 common approaches, and they fail differently. You can generate a random string and check the database for a collision, which is simple, but every write now costs a read, and it gets worse as the table fills. Or you take a global counter and encode it in base 62, which gives you 7 characters for about 3.5 trillion links, and no collisions by construction. But a single counter is a single point of contention, so you hand each API server a block of 10,000 IDs at a time, and it allocates locally. One honest downside is that sequential codes are innumerable, so if links must not be discoverable, you either scramble the counter or go back to random with a check. Now the cache, and this is the part worth spending your remaining time on, because at 4,000 reads a second, the cache stops being an optimization. Use cache aside. So on a miss you read the database and populate the cache. And because a mapping essentially never changes, you can set a very long time to live. Link popularity is extremely skewed, so a small fraction of codes serve most of the traffic, which means even a modest cache gets you a very high hit rate. And once the hit rate is that high, the database is no longer serving reads. It is durable backing behind the cache, which is a sentence worth saying explicitly. Now break it on purpose, because volunteering the failure modes before you are asked is the strongest single move in a system design interview. First, a single viral link lands on one cache node and melts it. So you either replicate the hottest keys across nodes or push them out to the edge. Second, when a hot key expires, every request misses simultaneously and they all hit the database together, which is a cache stampede. And you fix it by having one request refill. Third, a single region means somebody in Australia pays 200 milliseconds before anything happens, so redirects belong at the edge, rather than in one data center. Fourth, one database is fine at this scale, but say what you would do at 100 times, which is shard by the short code itself, since every lookup already has it. And fifth, if you are counting clicks, never write to the database on the redirect path. Publish an event to a queue and aggregate it somewhere else entirely, so the shape is always the same. Clarify the requirements, estimate roughly, sketch the boxes, go deep on the one interesting component, and then break it yourself. And it transfers, because a pastebin, an image host, and a feature flag service are all the same read-heavy lookup problem, wearing different clothes. So do not memorize this answer, run this process, because the process is the thing they are actually scoring, and it works on the prompt you have never seen.